Using a Linux server, we can provide services that are essential to a network. I'm Scott Simpson, and in this course, I'll show you how to perform some network administration tasks that a system administrator should know about. We'll take a look at configuring a Linux server to act as a DHCP server, handing out IP addresses to clients on our network. And we'll look at providing network boot capability for clients using PXE Boot. I'll show you how to configure a web proxy in order to save bandwidth and better control your client's internet usage. And we'll set up DNS and have a look at configuring mail. Many of these tasks are frequently handled by dedicated hardware, but we can also configure a Linux server to offer all of them. Let's go. In this course, I'm using two Ubuntu virtual machines, one configured as a server and one configured as a client. I've assigned them both static IP addresses for the time being, and the clients are both on the same virtual network, 10.0.20/24, running inside of VirtualBox. This network has access to the internet through the virtual router that VirtualBox provides us. I'm using a virtual network because some of the things we'll be doing could affect a production network, and we don't want that. The VirtualBox software offers a DHCP server as a feature, and for this course, we need to turn that off. When we configure a NAT network, there's an option to disable DHCP. That's great, but there seems to be a bug in the software that makes the software not respect that setting until the host system is restarted. So if you've been following along with other courses using a similar configuration, you'll need to take a moment and disable that setting before continuing here. Uncheck the checkbox, and then restart your system. Otherwise, you'll get different results than me in the video about setting up our own DHCP server for this network. Because we're pretty far along in this series, I'm making a few assumptions about your skill level at this point. I'm assuming that you already know how to modify network settings on Ubuntu. So if not, take a look at the networking course that covers that. I'm also assuming that you're comfortable working at the command line, and that you know how to troubleshoot something that goes wrong by looking at logs and at the manual pages. In order to communicate on an IP network, clients need to have an IP address. Addresses can be assigned manually, which is a good idea for things like servers and infrastructure devices, where you need to know exactly which address is being used. But most clients, like laptops, desktops, mobile devices, and Internet of Things, don't really need to have a specific address. They just need an address. On a network, the system that assigns addresses is called a DHCP server. DHCP, or Dynamic Host Configuration Protocol, usually runs on a router, but it can run on a separate server as well. DHCP keeps track of addresses that are in use and responds to requests from new clients with an address to use. And it can provide some configuration information to its clients. At a high level, DHCP works like this. When it needs an address, a client sends a broadcast message called DHCP Discover to the network, and a DHCP server that's listening for these responds with a DHCP offer message. The client responds with a DHCP request message, asking for that IP address. And then the server sends a DHCP ACK message to acknowledge the receipt of the address. Then the client uses that IP address until the predefined address lease time expires. We have a lease, so assigned addresses aren't used up forever. If a client goes away, its address can be reassigned to a different machine after a period of time. In this video, we'll set up a DHCP server on a Linux host and configure a client to use DHCP to get an address. One word of warning here though. While the other services we can set up on a network don't necessarily affect the network while we're experimenting with them, DHCP has the potential to really cause issues if it's set up on a network that already has another DHCP server running on it. In fact, this scenario, which is called a rogue DHCP server, is one of those things that keeps some network administrators up at night. It can be hard to troubleshoot, and it can cause clients to be unable to connect to network resources. So while you're learning, be sure you're using a virtual network without any chance of overlapping your real network. Or work with your network administrator to isolate the network you're using from the rest of their network. For this course, I'm using a virtual network in VirtualBox, and the VirtualBox software provides its own DHCP server. I've disabled that feature on my virtual network. To get started, we need the ISC DHCP server package. ISC stands for Internet Systems Consortium. Once that's installed, there are two files we'll need to modify in order to make this system act as a DHCP server. These are etc default ISC DHCP server and etc dhcp dhcpd.conf. In the ISC DHCP server file, we'll need to set the interface where the service is listening. The DHCP service listens for broadcast messages, so it needs to listen to a network interface, not a particular network address. And in the dhcpd.conf file, we'll set all of the other options, like the subnet that we're assigning addresses for, the range of addresses, and other options, like which router and which name server a client should use. So let's take a look at what we want to accomplish. We'll listen on the server's network interface called ENP0S3, the Ethernet interface. If your server has more than one network interface, you'll need to determine which of them you want to offer the service on. You can set more than one. And we'll operate on the 10.0.2.0 subnet. with a net mask of 255.255.255.0. We'll offer up 200 addresses, running from 10.0.2.20 to 10.0.2.220. That leaves a little bit of space at the beginning of the range that we can use for static addresses. And we'll offer up the router 10.0.2.1, so our clients can use that to access the internet. And we'll offer the DNS server 10.0.2.1 as well, so our clients can look up host names for other systems. Here on my server, I'll install the software. With apt install isc-dhcp server. Then I'll open up etc default isc DHCP server. And down here at the bottom, I'll set the interface to enp0s3. And I'll save the file. And now I'll open up etc dhcp dhcpd.conf. And here I'll set the other options. There are quite a few templates for different configurations in here, from a basic configuration that treats all clients the same, to individually specifying hardware addresses to give particular computers, and more. But for now, we'll make a basic configuration that treats all clients asking for addresses the same, placing them on the same subnet. But if you're curious, take some time and explore the other settings that are commented out to get some ideas about what else you can do. It can also be a good idea to make a copy of this file before you edit it, in case you feel the need to erase all the comments and just put your directives in here. I'll uncomment this line in order to make this server authoritative. Generally speaking, when you're setting up what will be the only DHCP server for a network, you want it to be authoritative. Up here, there's some defaults for the DHCP server as a whole. These will apply to clients on any subnet that the server offers addresses for. They can be set for individual subnets as well, or they can be set globally. I'll comment those out for the time being. Default lease time is the number of seconds that a client will get to use the assigned IP address before it needs to contact the server to renew, or before the address goes back into the pool of free addresses that can be used again. Depending on your policies and strategy, you can set this to a low number to be aggressive about reclaiming addresses. That's a good way of conserving limited addresses if you have an environment like a coffee shop or other public space, with many clients coming and going, using up your addresses. Or you can set it long if you want to help ensure that clients get the same address after a long period away from your network. It's up to you, and 600 seconds or 10 minutes is a reasonable default. Clients can also request different lengths of the lease, and by default, the maximum they're allowed to request of this server is 7,200 seconds, which is 120 minutes or 2 hours. Here we can redirect the log file if need be. And below that is where some example subnet declarations start. I'll make some space here and add in one for our 10.0.2.0 subnet. I'll write subnet 10.0.2.0 and netmask 255.255.255.0. Then I'll use an opening curly brace, and then I'll set the range of addresses from 10.0.2.20 to 10.0.2.220. And I'll end that line with a semicolon. Then I'll set the option routers and supply the router that will give our clients 10.0.2.1 and a semicolon. Then I'll use option domain dash name dash servers and put our DNS server 10.0.2.1. And I'll end that with another curly brace. Each of these subnet declarations has a set of curly braces, and each directive within them ends with a semicolon. If you miss one, you'll see an error in the log when the DHCP service tries to start up. We can put other options in here, like the domain name to append to client host names, which will end up as the search parameter in your etc resolve.conf file, or NTP servers to use, and more. All right, now I'll save. And I need to restart the DHCP server to pick up these changes. I'll do that with systemctl restart isc DHCP server. And now this server is ready to hand out IP addresses. Configuring DHCP on a server like this gives us a lot of flexibility for the configuration of our network. It allows us not only to provide dynamic IP addresses for clients on a given subnet, but it also allows us to offer various services that we'll see how to manage throughout the rest of the course. Let's configure our client system to get an address from our DHCP server. Right now, this system is set to have a manual address. It's 10.0.2.11. That's not within our range of dynamic addresses. I'll open up the network settings and change them to get a dynamic address instead. I'll write nano etc network interfaces. I'll change the iFace line to DHCP, and I'll comment out the other lines. I'll save that, and then I'll restart. Now I'll take a look at the IP address of the system with IP A, and I can see that now I have an address that's the first one within our range, 10.0.2.20. Now, the address is within the range of the dynamic addresses offered by our server. The DH Client tool can tell us some information about this client's DHCP configuration. I'll use DH Client-R to release the lease, and then I'll use DH Client-V to request a new one. In this case, I got 10.0.2.21. Up here, we can see the interface that we're listening on, ENP0S3, and the MAC address of this interface. After that, we have the most recent few lines of logs that DH Client has generated. For a brand new lease, we'd see information about DHCP Discover, DHCP Offer, and so on. For an older lease, when it's being renewed, for example, we'll see DHCP Request and DHCP ACK. We can see that in this case, the client is requesting 10.0.2.21 via broadcast on port 67. It gets an offer from the server at this address here, and then it acknowledges the receipt. Then it sets its own IP address to the address given to it by the server. When you're working with DHCP and things aren't working quite right, there's a few things you want to make sure to check out. First, be sure to use DHCP Client-V to make sure you're getting a lease from the correct server, and that there's no errors in the log shown there, or in the syslog. You'll also want to check out the status of the DHCP server, and take a look at the logs there to see if they indicate any particular problems. One problem that can arise is an overly restrictive firewall. DHCP uses UDP port 67 on the server and UDP port 68 on the client, so double-check your firewalls. Usually a client won't forbid outgoing traffic, but it never hurts to check. Once your systems are configured to get addresses through DHCP, you don't have to worry about setting static addresses for them. PXE, or Pre-Boot Execution Environment, allows a system to boot using a software environment provided over the network, rather than from a disk attached to the local system. This kind of booting environment is used widely for installation, deployment, and remote booting in labs and data centers. PXE relies on DHCP, or Dynamic Host Configuration Protocol, and TFTP, Trivial File Transfer Protocol, in order to work. DHCP provides an initial IP address for the system and tells the client where to find a TFTP server that hosts executable operating system images. TFTP is a bare-bones, no-frills file server that's commonly used in many different applications, ranging from network booting to hosting other software for the purpose of updating device firmware. Let's configure our server to act as a PXE Boot Server. We already have a DHCP service set up, so we'll add a few more things to make a complete PXE Boot solution. We'll install and configure TFTP, and then we'll copy some bootable files from an installer. Then we'll reconfigure our DHCP server to enable network booting for clients, and we'll provide a configuration that hands the client off to the TFTP server to get its boot image. Here on the server, I'll install the TFTPD-HPA package. This creates a configuration file at etc default TFTPD-HPA that contains the basic information for running the daemon. Let's take a look at that. Here I can see that the service is running on port 69. TFTP uses the UDP protocol, like DHCP, and I can see the directory that TFTP will serve files out of. For a more advanced setup, you can change the options here, but I'll leave them alone. This storage folder is really only intended for files that will allow our clients to boot up. In this video, we'll focus on hosting a basic bootable installer to allow clients to install over the network. In a thin client setup, like a lab or some data center applications, you might want to provide storage for user home folders or caches or something like that, where clients will write back to a file store. So if your setup needs any kind of persistent storage, like an NFS export or some other kind of file share, you'll need to set that up separately. Now I need to download an image from which I can get some files that will let me netboot clients. I'll download the Ubuntu server image here. Now I'll mount it. First I'll create a mount point, and then I'll mount the image into that path. And then I'll copy the contents of the install netboot directory into the var lib tftp boot directory. This will give me a bootable installer, which will install the core of the operating system from a mirror on the internet, and then present me with choices to install all kinds of other software collections, like Ubuntu Desktop, various server components, and so on. The final step in our PXE Boot setup is to add some configuration lines to the DHCP configuration file, in order to allow that server to act as a PXE Boot server for our clients as well. I'll open up etc dhcp dhcpd.conf, and here in the declaration for this subnet, I'll add a couple of new directives. I'll write allow booting and allow bootp. Then I'll write next server 10.0.2.10, which in this case happens to be this server, Or if you're running TFTP on a different server, you'd put in that address instead. And then I'll write file name pxelinux.0. That's one of the files that we copied from the installer, and that'll act as the boot environment. I'll save this. Then I'll restart my DHCP service and the TFTPD service. Then I'll switch over to my client here and restart it, and then I'll choose to start it up from the network. I'll reboot, and as it's coming up, I'll press F12, or function F12 on some keyboards, to choose the boot method. If you're using a real computer, the key you'll use to go into the boot setup may be different. Or if you're booting a system with no other bootable media, it might go to the PXE Boot environment right away. Bringing up this menu here on VirtualBox gives me a few options, and I'll choose L for LAN. Here's the PXE Boot process running from the network card, or really the emulated network card, and it's waiting to get a DHCP address. And here we go. This is the minimal installer booted from our server on the network. I won't go through the installation process here because it'll take a while, and this system already has an installation. But if you go through the process, you'll see that the core part of the OS will be installed over the internet, and then you'll get a chance to choose what kind of system this new installation will become. Anything from a very basic server to a multimedia workstation. With these basics in place, there are many ways you can customize the boot environment to suit your needs. You can choose to host images on an HTTP or NFS server, and add menu entries to the boot configuration to support that, along with kickstart files to point to the installer locations. You can create network bootable live environments for thin clients, and you can even configure a PXE Boot Server to host many different images for many different system architectures. You can modify the DHCP settings to provide different installers based on the subnets your machines are coming from, and more. Using an HTTP proxy server, we can control or redirect client network activity. Usually, a proxy is used for web traffic. Proxies are common in organizations and enterprises, where they can be used to help monitor or manage traffic. And they can be used to cache frequently needed content and resources on slower or metered connections, to prevent wasted bandwidth from repeated downloads of the same file. Proxies can also be used by clients to avoid organizational traffic policies and limitations, so even if you don't plan on using one on your network, you should know how they work and what to look for. The software we'll use to set up an HTTP proxy is called Squid. Squid is often used as an HTTP proxy on its own, and it can also act as a caching proxy. As an HTTP proxy, Squid takes requests from clients and then retrieves the needed resources from a remote server. Then Squid returns those resources to the client system. An HTTP proxy makes web requests and acts as a stand-in for remote web servers. This is different from a router, which passes packets between networks. Using a proxy gives us the opportunity to log web activity and to potentially block access to certain remote sites. As a caching proxy, the server can store documents and information that come as part of the reply back from the remote resource, in case they're requested again by the same client or a different one, in order to save bandwidth and traffic to the remote resource. Squid can do this for HTTP and HTTPS resources, DNS responses, FTP resources, and more. We can offer this service to any client that tries to connect, and we can also limit access to particular users or a particular network range. And we can choose to block access to particular resources if need be. While Squid proxies are generally used for outbound traffic from a network of many clients, they can also be used to relieve the load on web servers by caching content from that server to serve up to many clients. That's called a reverse proxy. Let's take a look at installing and configuring a Squid proxy for a local network. I'll install the Squid package with apt install Squid. Then I'll take a look to see if the software is running with systemctl status Squid. I can start it up if it's not auto-started, but mine's running. When it's running, Squid operates by default on port 3128, so if you're using a firewall, be sure to allow access to that port appropriately. The configuration for Squid is managed by the etc squid.conf file, which we'll look at in a little bit. It has very extensive comments and examples, which is helpful, but means there's a lot of lines to scroll through if you're looking for information about specific settings. Squid keeps logs in the var log squid folder. And in there, you'll see the access log, which keeps track of client requests, and the cache log, which provides information about the state and the usage of cached files. Squid keeps its cache of files in the var spool squid folder. And of course, all these things can be customized to suit your particular needs. I encourage you to take some time to look through the squid.conf file and read the comments there. Before we make any configuration changes, let's configure a browser to use the Squid proxy so we can see how it works. Here in Firefox, on my server, I'll go into the Preferences, and I'll search for the proxy settings. I'll choose to use a manual proxy configuration, and then I'll put in localhost and 3128. I'll use this proxy server for all protocols, and I'll press OK. Now I'll go visit a website to give the proxy something to do. I'll visit engadget.com. Back here in the terminal, let's take a look at the access log. Cat var log squid access.log. Here's every request that I made over HTTP listed with a miss. We didn't have anything in the cache when the server started, so that makes sense. And here's the HTTPS requests sent through tunnels rather than cached. A Squid server can be configured to intercept and read these requests, but in this configuration will respect the user's expectation of privacy when connecting to secure sites. It can be surprising to see how much traffic comes from what's arguably a simple request. You'll get every request to tracking scripts, remote resources, and in many cases, activity from the client browser doing telemetry and trying to prefetch and predictively load search results and top bookmarks. A lot of this goes unnoticed by end users with fast connections, but it can add up to megabytes of traffic that's not really ever used for anything. And across hundreds of clients on your network, that wasted traffic can add up fast, especially if you're on a metered or slow connection. As I mentioned, there's a lot in the configuration file. It's probably 99% comments, which makes it somewhat easier to find out the particular options and syntax you might need to use to modify a feature. I'll open up the file with nano etc squid.conf. There is a little bit of information already specified in this file, in particular the settings for SSL ports and safe ports, the ports which Squid will allow a connection to. Further down, there's also settings for HTTP access, where we can set the behaviors of the HTTP proxy based on the port definitions. For example, here, the server is denying HTTP access to any ports that don't appear in the safe ports list. Anything that isn't specified has some default settings, so anything you add in here will change the configuration from the default. Many of the options you'd want to make a change to are already present in the file, but commented out, making it easy both to look through comments and to search for directives rather than starting out from a completely blank file. By default, Squid runs on port 3128, as I mentioned before, and keeps its cache of documents in memory rather than on the disk. It allows anyone who connects to make requests. These are all configurable, in addition to many other more advanced options. Dedicating RAM to cache storage gets a fast response, but it can be expensive. Let's set the server to store its cache on the disk instead. Here I'll search for the directive cache_dir. It appears many times in the comments, and I'll find the instance where it's commented out and uncomment that. In order to understand the syntax and the other options that are available, I can look at the comments above it. The first argument here is the storage format. UFS is the default, and if I wanted asynchronous access, I could use AUFS. Depending on your performance needs, you could switch to that. The next argument is the path where the cache will be kept. And following that, there's a specification for the maximum size of the cache in megabytes. I'll keep this at 100 megabytes right now, but on a large deployment, you might want to make the cache larger to keep more documents. A large cache can help to accommodate large repeated downloads, like Linux installation ISOs. If you're running a dedicated proxy server for an organization, you might even dedicate whole disks to cache. You can add additional paths by adding a line here in the configuration for each one. The arguments after the size are how many folders to use in the cache at the first level and then at the second level. These are the defaults, 16 folders at the first level, and within each, 256 folders. Unless you have very specific needs, it's probably a good idea to leave these as is. As you customize your setup, you can tweak things like the algorithm that Squid uses to determine what to keep in cache and what to discard once the allotted space starts filling up. I'll save this, and then I need to restart Squid in order for my change to take place. Unlike many other services, restarting Squid takes a while, unless you configure it not to. It's waiting for outstanding requests from clients that might be in the middle of an interaction with the server. After 30 seconds, the service will be restarted. All right, now let's go reload the web page. Let's move into the cache directory and take a look around. All right, cd spacevar spool squid, and here I can see the top level folders that are holding my cached files. Our proxy is working, but it'll only allow connections from the local host right now until we configure some security settings. We'll do that in the next video. Because a proxy server accepts and generates traffic, it's a good idea to ensure that it can only be used by authorized networks or users. Without any additional configuration, our Squid server accepts traffic from itself, but no other systems. Let's configure another system here to use the server as a Squid proxy. Here on the client machine, I'll open up Firefox. From the menu, I'll choose Preferences. I'll look for the proxy settings, and I'll set this client to use my server as a proxy with 10.0.2.10, port 3128. Then I'll try to browse to a site. I see an error message saying that I'm not allowed to use this proxy server. We'll need to make a configuration change to allow it. Let's switch back to the server and jump into the configuration file to see how to do that. I'll write nano etc squid.conf. I'll search here for a term that I know we'll be using, localnet. And I can see there's some examples here on how to write an ACL. I'll add a line here and start writing my own line. ACL to add a new access control list, and then a name, localnet. And after that, I'll write src to tell the Squid server that the address range that I'm going to give it is a source. Then I'll add my network here, 10.0.2.0/24. We can add all kinds of things as ACLs, not just a source network. We can add time ranges, URLs, AS numbers, protocols, methods, and more. We'll use the ACL to tell Squid what to allow, so let's do that next. Below the ACL listing in this file, there's a descriptive block about how to do that. I can write HTTP access, and then put in an ACL name or negate an ACL name with an exclamation mark. Again, I'll add some space in here, and I'll write HTTP_access allow localnet. The HTTP access directive tells Squid that we're talking about how a client can be permitted to use HTTPS, HTTP, and FTP sources. And allow localnet says to allow clients on the localnet access to these services through the proxy server. I'll save this and I'll restart the proxy server. Remember, it'll take a little bit because it's waiting for connections that might be open. All right, I'll switch back to my client and try to browse to the website again. This time it works because the client is on the local network that's allowed to access the proxy server. We can add another layer of security as well by requiring that the people using the proxy server log in with a username and password. I'll switch back over to the server here. Whereas adding access for clients of a specific network could be handled with 2 directives, adding user-level access is more involved. We can use Apache Basic Authentication to configure users who will be able to access the proxy. To get the software we need, I'll install the Apache web server. With apt install Apache 2. Then I'll use the ht password command with -c to create a list, and I'll put the list at etc squid password. And then I'll specify the user that I want to create an account for. I'll set a password and verify it. And then that user's been added. To add another user, I'd use the same command, but without the -c. Then in the configuration file, I'll take a look for the section with the auth param tag. There's a lot of notes here about the configuration, including what the prompt will say, how long the authentication will last once the user logs in, and more. I'll jump down to under my ACLs to my safe ports section. And below those, I'll make some space, and I'll add a few lines. I'll set the authentication parameter to basic. And then I'll set the program that we'll use to usr, lib, squid, basic, and CSA, auth. And then I'll give that the argument of the list that we created with the users, etc squid password. Then I'll create an ACL called auth users and say the proxy authentication is required. I'll add an HTTP access line to allow access to that ACL. And then I'll save. And I'll restart the Squid service. I'll open up a web browser again. And now, back on the client, if I try to browse to a website, I'm asked for credentials. Once I enter them, I can browse until the authorization expires, which is a parameter that's configurable in the squid.conf file as well. In order to get more familiar with how the access control settings work, try setting up your proxy to deny access between certain hours, or only to certain browsers. Everything you need to get started is listed in the configuration file comments. If you want your clients to automatically use the proxy server you configured, you can configure a PAC file, or proxy autoconfig script. This is a small JavaScript file hosted on a web server, where a client can find it and use the contents to automatically configure a proxy. This can be especially helpful if you want the ability to point clients at a different proxy after you set up your infrastructure, if you want to define more than one proxy server, or if you want to control which proxy a client uses based on their network address. Let's start out here on the server by creating a basic script. All right, nano var www html proxy.pac. And here, I'll write function, find proxy for URL, and give it the arguments URL and host. Then I'll write return proxy, and the IP address of my proxy server, in this case 10.0.2.10, port 3128. And I'll close the curly brace. Now, in the browser's proxy configuration area, I can choose Automatic Proxy Configuration URL and put in the URL for my proxy file, 10.0.2.10/proxy.pack. I'll close my browser and open it up again. And now my browser is aware of the proxy server because of that script, not because I've explicitly tucked it in. Browsers will check for updates to this file periodically, so you can use this to keep your proxy setup a little more flexible. When we communicate with a server on the internet or on our network, the communication happens using IP addresses, numeric designations that the IP protocol uses to transmit and route data. But IP addresses aren't terribly human-friendly to remember and type, and sometimes more than one server might handle a given service. So luckily, there's a system to associate human-readable names with the IP addresses. This is called DNS, or Domain Name System. This system can work at various levels. At the smallest level, we can set up a hosts file on our computer that provides a manual association between a name and an IP address. And Linux systems use a tool called DNSMask to act as a local DNS resolver. And while it's okay to maintain on one system, it can get pretty tedious to maintain across many systems in an organization. For a local or organizational network, we can configure a name server like Bind, or Berkeley Internet Name Domain, to keep track of the names of resources within a network and their associated IP addresses centrally as a service. And this works for the servers we know about. Our servers might have information about systems within our network, but for anything outside, on the internet, the DNS servers still need to communicate with other servers to get the information their clients want. At the internet level, the mappings for top-level domains like .com, .co.uk, .de, and so on are handled by clusters of name servers called root name servers, and they're constantly updated as new websites appear. Every website out there on the web has a DNS server serving a zone file for it. These zones make up the information the DNS knows and which DNS servers provide to their clients. In this video, we'll take a look at maintaining a DNS zone for a local network. Typically, a zone represents a particular domain, like yourcompany.net or example.com. It can also represent a subdomain. We'll use example.com here, which is a domain set aside by ICANN for documentation purposes. If you have your own domain name, you can use it here too. Before you do that though, I want to make note of a recent change. For a long time, administrators used domains ending in .prod, .dev, .home, and so on for their test networks. That approach worked well because prod, dev, home, and the like weren't real top-level domains. But recently, ICANN, the organization in charge of names on the internet, has decided to make them real TLDs. So that means someone could actually go and register test.dev and it would be a real domain. So for the time being, you'll see some unexpected results if you use these domains. One of the places you'll see this is in the reported addresses of systems using these domain names. If you see the address 127.0.53.53, that means you're using a domain that ICANN has decided to make available at the internet level, and they're warning you about it. 53 is the port that DNS uses, so this address is a nod to that, making it clear that you're dealing with a DNS issue and not something else. It's always a good idea to use a real domain you own, but if you don't have one, you can use a made-up TLD, like testing.myreallycooltestdomain, or mynetwork.isn'treal, or anything else that doesn't appear in the ever-increasing list of valid TLDs. Wikipedia has a great list if you're curious. You can, of course, also use an existing domain, as it will do with example.com, but that will remove the ability of clients on your network to connect to the real version of that domain. Generally, you don't want to spoof a domain like that. It's a little bit fraudy, but example.com is reserved for this kind of thing, so it's all right to use. The first thing I'll do to set up a DNS server to handle my zone is to install the bind9 package on my server. apt install bind9. Installing this package gives us a few files that the server uses to define how it works. Before we make any changes, let's take a look at them. I'll write ls-l etc bind. Most of these files are called db something or named something. Named is the name daemon that does most of the work within the bind suite of utilities. named.conf is the primary file here, and it just references other files. This is a common pattern with Linux utilities, and it can be interesting to go exploring what each of these files does. The contents of these files can also be put into the primary file here, but this arrangement helps keep things organized. The named.conf.options file is the place where you could set options for the DNS server. We'll work with this in a little bit. named.conf.local, likewise, is a place where we'll make changes when we add a zone, and we'll take a look at that soon also. And named.conf.defaultZones gives the server information about the default zones. Up here, it's importing a file called db.root to provide information about the zone called dot, which is the top level of the DNS hierarchy. The db.root file has information about the global root servers that are authoritative for top-level domains. And below that, there's information about the localhost forward and reverse zones. We won't be changing anything in this file. It's important for our DNS server to know about the root servers because ultimately it needs to be able to query for top-level domains itself in case a client asks for information about a server that it doesn't know about. The db files here are where we'll define zones when we get to that. As I mentioned, db.root is the listing of the root servers for the top-level zone. And db.local is the information for the local loopback. db.empty is a file we'll duplicate and use to configure our new zone. I want to configure this server to provide information about the example.com domain. This DNS server will provide information that other clients will rely on in terms of which IP addresses are linked to the domain name. We'll set up what are called forward and reverse zones. A forward zone will take a name like example.com and resolve it to an IP address. And a reverse zone will let us take an IP address and look up a name that it's associated with. First, I'll edit my named.conf.local file. Here, I'll add an entry for a zone, and that'll be example.com. The type is master, and we'll point this to the file etc bind db.example.com. I'll also add my reverse zone with 2.0.10.in-addr.arpa. This is master as well, and the file we'll point it to is etc bind db.2.0.10. I'll explain what those numbers mean in just a minute. I'll save this file, and looks like I forgot a semicolon up here. And it's important to make sure that you double check, put the semicolons in where they need to be. At the end of each of these curly braces, I'll need a semicolon. I should note here that these names don't need to be formatted exactly like this. The files can be called whatever you want, and they can be organized in folders if you'd like. But naming them that way follows the convention used in the package we installed, so I'll go with it. Now we need to create the zone files that the conf file references. This file is a little bit detailed, so I'll describe things as we go along. First, I'll create a copy of the db.empty file. I'll call that db.example.com. We can delete these comments because we have copied the file, we followed those directions. Here at the top of the file is a TTL. This is the default time to live, or how long the record will be valid before a server needs to request it again. Here on the next line, we set our domain name, example.com, with a period at the end. This is called the origin. The dot at the end of the domain is important because it indicates that this is the highest level domain that we're specifying in the zone. This is the domain this zone defines. After that, we'll use IN as the record class. IN stands for internet, and it's really the only one you'll see in common use. After that, we have SOA, meaning start of authority, and the primary name server for this domain, which in my case will be servervm.example.com. And again, this ends with a period. Then we'll set the contact email address for the person responsible for DNS on this domain. We'll call that person DNS admin, and we'll replace the @ with a dot. So we'll have dnsadmin.example.com. The @ sign has a special meaning in these records, and we don't want to cause problems using it here. After that comes a set of parentheses with some numbers inside. The first number here is the serial number. Usually it's a timestamp, incremented at the end whenever the zone file's changed. Incrementing this number tells other servers that the record has changed and that they should read the new information. The next number is the refresh interval in seconds. This is the period after which a secondary or slave name server should reload the record here, regardless of whether it's been updated. The third number is the retry value, a number of seconds after which the DNS server should try to read this record again if it failed the first time. The fourth number tells a slave name server how long this record is considered valid if it's unable to read updates from the master server. And the fifth value is the negative cache TTL, that is, how many seconds we're allowing other servers and resolvers to cache a name error if the record has expired before checking in again. And that ends with a closing paren. This next line starts the NS section. This is where we indicate name servers for this domain, one per line. The @ here represents the origin, so in this case it stands for example.com. Again, we have IN for internet, NS for the record type for name server, and then the fully qualified domain name for a name server in this domain, in this case, servervm.example.com. If you have more than one name server for your domain, you add a line for each address. You'd add the slave name servers in here as well, if you're using them. So they're published and clients reading this record would know to go to them if they can't resolve the primary or master name server. After that, we'll define the A record, or address record, that will map names to IP addresses in this domain. I'll set the first entry here to @ to mean that we're talking about the origin, or the domain itself. I'll add IN, and then the A type, and then I'll put the IP of my server, 10.0.2.10. That'll respond to the queries for example.com with this IP. Customarily, you wouldn't want your name server to respond to your top-level domain. That's usually reserved for your website, so you might want to put the IP of your web server in here instead. And on the next line, I'll add an entry for this system, server-vm in A 10.0.2.10. You can add a record here for anything that you want to have a specific name-to-IP mapping. You can also add other record types, including text records, service records, and MX records, as we'll see in the chapter about mail. And we can add a CNAME record, or canonical name, to point a different name to the same server. For example, I can make www point to my server here, with IN, CNAME, and then the A record name of my server. I'll save the file. Now we need to set up a reverse zone file. This will let us look up a host name by IP address instead of the other way around. This is used in various applications, like verifying mail. Once more, I'll copy db.empty, and I'll name it db.2.0.10, and I'll edit it. The name I chose, 2.0.10, probably doesn't make a lot of sense. It's the first 3 octets of the network we're providing name service for, but backward. Basically, the way reverse DNS works is to treat an IP address like a domain name, but reordered in the order of specificity. If you think about a domain name like www.example.com, the www part is the most specific, probably only referring to just one computer. And example is a bit larger, our whole network. And com is the top-level domain which contains example, which contains www. IP addresses are the reverse of that. In 10.0.2.10, the last .10 is the most specific, referring to one computer. The 2 refers to the subnet that we're on, 0 is another subnet, and the first 10 is a whole block of IP addresses. So if we reverse the order of the numbers, we have a way of talking about the specificity of things in the same way as DNS. So that's where that comes from. Easy, right? Well, it can take some getting used to. Here in my zone file, I'll set the origin to 2.0.10.in-attr.arpa. In the SOA record, I'll specify my name server, server-vm.example.com. And again, I'll set the contact information, dnsadmin.example.com. And then, instead of A records down here, we create PTR, or pointer records, mapping IP addresses back to host names. I'll add 10 here, the last octet of my server's IP address, and use IN, PTR, and the fully qualified domain name of my server, servervm.example.com. If I had another server at, say, 10.0.2.11, I'd put 11 in PTR and its host name. All right, I'll save this file. And then I'll restart the bind9 service. Now, I can use the dig tool to look up addresses using this server. By writing at 10.0.2.10, I can tell it to use my name server. And I'll look up a record. Let's say server-vm.example.com. And there we go. We get an answer back. servervm.example.com is 10.0.2.10. Let's take a look just at example.com. Once again, this server is providing that. Now that we're providing DNS services on our network, we can update our DHCP configuration to automatically provide this DNS server to all of our DHCP clients, or at sudo nano etc dhcp dhcpd.conf. And down here, where we define the name servers, I'll change this to the address of my new DNS server. I'll save the change, and then I'll restart the DHCP server. With systemctl, restart, ISC DHCP server. Now, if I restart the networking on my client, I'll get a new DNS server, and I can write dig servervm.example.com, and I get the information served by my new server. There are 3 primary types of name servers, and we've already configured one, an authoritative name server. It knows about our domain, but it isn't configured to respond to queries for sites outside of our domain. If clients were to ask it for, say, google.com, it wouldn't be able to return an IP address for that client to browse to. And in some configurations, that's exactly what we want. We can direct clients to use more than one name server, and sometimes we want there to be separate authoritative name servers for internal use. But if you're wanting to use the name server for general purpose resolving as well, or if you've just set up a brand new name server with no configuration, you can configure it to act as a caching or forwarding name server so it can contact other servers that hold information about other sites. Both configurations actually cache information, but they handle looking up information differently. What we refer to as a caching name server looks up information for clients itself by performing recursion across multiple DNS servers. If it doesn't know the answer to a question from a client, it refers that question to another DNS server, which can then refer it to another server and so forth. When an answer comes back, the caching name server keeps a copy of the reply to serve up to clients, and then sends the information back to the original client. A forwarding name server doesn't take the time to do this recursion operation itself. Instead, it sends the request to a different server to handle it. And when the reply comes back, it still keeps a copy in its cache for other clients. Let's configure our DNS server as a caching server, and then as a forwarding server. These are configurations that we can make to a server with existing zone records or to a clean install of a bind server. Here in the etc bind named.conf.options file, I'll set the option for recursion to yes. This is the default, but it's good to set explicitly. You can also configure a system to not perform recursion if you don't want it to do that. Often, recursion will be set to no on authoritative name servers. Then, in order to be security-minded, I'll use a parameter called allow query. This takes arguments in curly braces. Those arguments can be networks, individual hosts, or some keywords. In order to keep things organized, I'll define an ACL, an access control list, called allowed, and I'll put my networks in there. I'll write 10.0.2.0 /24, localhost, and local nets. Local nets tries to automatically allow clients on the local network access to the server for looking things up, but I'm also specifying it explicitly. And with that ACL defined, I'll put it into my allow query block. So those clients will be able to use this server. I'll save the file, and I'll restart the bind service. Now we're at dig, and we'll use this server, 10.0.2.10, and let's look up, say, google.com. And there's a response. I see the A record, name server records, and some additional information. And I can see that the query took 732 milliseconds. If I recall that same command and ask my server for Google's information again, now it's basically instantaneous because it's coming from the cache. The caching server will use its local copy of this information until the TTL period for the record is up. And then, when someone asks for the information again, the server will go recursively find the updated information. Recursion takes a decent amount of resources and bandwidth when there are a lot of clients asking for information. So DNS servers can be configured to push off that traffic to another server in order to save bandwidth or avoid lags from slow connections. To do that, we'll set up a list of servers that this server will forward its queries to. We'll do that with a forwarders block, which is already defined here in the options file, but is commented out. I'll replace this with 2 of Google's public DNS servers, 8888 and 8844. I'll save this file, and I'll restart the bind server. And now, when I query for a domain, my name server will send the request to Google's DNS servers to perform the recursion rather than taking care of it itself. In the real world, you'll come across various combinations of DNS servers. Using one server to do everything is fine for testing and learning, but as an organization's network gets larger, it's necessary to split up DNS functions in a few different ways. In fact, if you consider our server we just set up here, it doesn't make a lot of sense. It's authoritative for our domain, but any external client asking it for a server on our domain, for example, a web server, wouldn't get a really useful response, because right now, it would be pointed to an IP address internal to our network. So we need to have the authoritative server exposed to the internet, pointing to the public IPs of our web server or our load balancers or something like that. And then we'd set up a caching or forwarding DNS server inside our network to provide a fast local cache and reduce bandwidth usage, possibly with another authoritative server on the inside. For internal sites like an intranet or a development environment, depending on the size of your organization, your traffic patterns, and your security requirements, you'll need to plan out a DNS solution that suits your needs. For a deeper dive, take a look at some of our other DNS courses, like Managing DNS Essential Training and Linux, Bind in DNS. Mail is an important service on the network. A lot of system services rely on it or make heavy use of it. Even if the messages are only for local delivery, mail makes a lot more sense than most other ways of delivering text information to various destinations. Mail works using a few components. A mail transport agent, or MTA, accepts mail messages from users, programs, or servers and clients, and sends the messages to the correct mail servers. A mail delivery agent, or MDA, makes mail messages on those servers accessible to users via the IMAP or POP3 protocols. And an MX record on our name server points mail agents and clients to the correct server. We can set up mail locally with these components, and if our mail server is exposed to the internet and configured to accept incoming mail, we'd also put MX records in our zone file to advertise the location of our mail server for outside senders. A common MTA that we'll install and configure here is called postfix, and a common MDA is called dovecot. First, I'll install postfix on my system. With apt install postfix. During the install, I'm asked a few questions about how the system should work. The first prompt is what sort of mail server I'm configuring, and I'll choose Internet Site. This will allow the postfix server to accept mail from local and remote hosts using SMTP, the Simple Mail Transfer Protocol. Then I'm asked for the mail name. For sending mail between users here on this host, it's fine to leave this as the machine's host name. Then messages from the user Scott would be delivered from Scott at server-VM, or I can set it to my domain. So messages sent from my user will come from Scott at example.com. If it's important for your setup that the name of the host be in the address, set it that way. Otherwise, I'd recommend you set it to the domain, so you have normal-looking email addresses. The installation continues, and I can see some assumptions that it's made here about what domains to accept mail for, and what network ranges to allow access to. These can be changed in the configuration file or by using dpackage reconfigure postfix. This is a functioning mail server now, but before we do anything, I want to make a few changes to the configuration. The first thing I'll do is set the myHostName parameter here to my fully qualified domain name. This will show up in error messages, among other things, so it can be useful to set to a particular host's name. Or you can use your higher level domain here as well. Up to you. Messages that come into the system will be held in the var mail folder, and we can reconfigure that to put messages in a folder in a user's home folder as well. Depending on how you want your users to interact with mail and how you've designed your backup strategy, this might be a good idea. I'll set up a home mailbox in each user's home folder called mail. home_mailbox equals mail with a slash on the end. Right now, this host will receive mail for users defined on it. If you need to send mail to other networks or to other servers, you can configure the relay host directive here with an address for a mail gateway or smart host that can deliver to those systems. And I'll save this file. As it's configured right now, this mail server will work to send mail between users on this host. I can do that by sending a mail to myself here at the command line. I'll install a text mode mail client with apt install mud. But before we open up mud, we have a little bit of a chicken and egg problem. A mail reader will want to look for a place where mail exists, but we don't have any mail, so there's no place that mail exists. So let's create a blank mail folder here in the home folder, where both this client and the server will expect there to be a folder. I'll write mkdir-p mail, and we'll need to create 3 folders: cur for current, new, and temp. Now I can write mut-f mail. To send myself a mail, I'll press hem, and then I'll address it to myself, Scott at example.com. The subject, first email, and then mut takes me into Nano so I can compose a message. When I'm done, I'll save with Control-O and exit. I can preview my message, and then to send it, I'll press Y. I'll refresh the inbox with a $, and look at that, I've got a new mail message. I'll press enter to open it up. I'll quit mut with a Q key. Each user on the system will be able to receive mail through their username at the domain, but we can also set up aliases or secondary names that users can receive mail through. I'll set up an alias to receive mail through admin at example.com. That's not a real user, but we'll map admin to my account. I'll write hello, etc, aliases. Here I can see the postmaster is already an alias for root. I'll write admin and my real username. I'll save the file, and I'll run the new aliases command, pick up those aliases. Oops, need sudo for that. All right, again, I'll open up mud and compose a message to admin at example.com. I'll write a subject line, and compose a message. I'll send it with Y and refresh my inbox. And there's my message sent to my alias. Again, I'll quit. The last thing I'll do to make this SMTP server closer to complete is to add an MX or mail exchange record to my DNS setup. If I were offering mail capability on the internet, I'd need to add MX records to my public DNS server or on my domain registrar's site. But because this is just a local installation, I'll edit my local zone file so clients on my network can look up my mail server. I'll open up my zone file at etc bind dp.example.com, and down here under my A and CNAME records, I'll add @in mx for mail exchanger 10 and the name of the A record for my server. This looks somewhat like the other records. The @ means it will respond to the origin, the domain, example.com, IN for internet, and MX for mail exchange. But after that, this number represents the priority of the mail server. In a large setup, you'll ideally have a few mail servers acting as relays to store and forward mail if one of your mail servers goes down. Mail servers with higher priority have lower numbers, so this 10 here is pretty low. If I had a secondary mail server, I'd give it a priority of maybe 20, and so on. Depending on your needs, you can set your priorities accordingly. And then I give the host name of the system handling mail. This should be the host name or the fully qualified domain name with a period at the end, but not an IP address and not a CNAME. Okay, I'll save that. And I'll restart bind. So now we can read and send mail on this host. In order to be able to connect to this host remotely, like from a mobile device or a desktop system, we need to install a mail delivery agent that will provide a POP3 or IMAP service. I'll show you how to do that in the video about Dovecot. Now that I have a server that can receive mail, I'll install Dovecot, the tool that will provide an IMAP service that a client can connect to read mail. I'll write apt install Dovecot common and Dovecot IMAPD. The configuration for Dovecot can be complicated. Let's take a look at the configuration files and make a few changes so we can get mail in a mail client instead of at the command line. I'll change into the etc Dovecot confd folder. All of these files are included in the primary configuration, and they're broken up into pieces to make it easier to manage. The first change I'll make is in the 10-mail file, or a nano 10-mail. Here I'm going to change the mail configuration to match what we had in the postfix setup, or a maildir :tilde/mail. All right, I'll save that. And the next change that I'll make is in the 10-SSL configuration. I'll write sudo nano 10-SSL. If your IMAP server is internet-facing, you'll want to generate or buy a valid certificate to secure it. But for testing, we can just use the snake oil or a self-signed certificate. I'll uncomment SSL cert, and I'll change the path to etc SSL certs SSL cert snakeoil.pem. And I'll change the key to etc SSL private SSL cert snakeoil.key. And now that we have those specified, I'll move up here and choose SSL equals required. Then I'll save the file. And I'll restart Dovecot to pick up these changes. I'll switch over to my client system, and I'll install Thunderbird, a free email client from Mozilla. I'll open that up. In the configuration wizard, I'll choose skip this and use my existing email. I'll write my email address, scott@example.com, and give my password. Then I'm prompted to add a security exception. I'm seeing this because we're using the snake oil certificate, which is not a trusted certificate. This is fine in testing, but in production, you'll want to use a real certificate. I'm going to store this exception and confirm it. And now, if I click on my inbox, I can see my emails. I can compose a message by going to write. And when I go to send the message, I'm getting a security exception again. I'll permanently store this exception and confirm it. I'll try to send my message again, and there it goes. I'll choose Get Messages, and here's my new message. For a more in-depth look at how to configure email services, be sure to check out the course, Linux Email Services. After we've configured services on the server, it can be difficult to remember exactly what we've enabled and what roles the server is handling. We can sift through the services that are running with the systemctl command. But a quick way to see what network services the server is offering is to use the ss command with a variety of options. This command is used to see which sockets are in use. And with the options A, P, T, and U, we can see which ports are open and which processes are using them for both TCP and UDP. Adding the N option, we can tell the system not to guess what's running on a port, but rather give us the actual port number. I can see here on this server, I have something running on port 25, that's my SMTP server. Something on port 3128, that's my Squid server. Port 143 is hosting an IMAP login, that's my Dovecot. Port 53 is listening for DNS traffic with named. And scrolling up into the UDP section, I can see that I have DHCP running on port 67 and TFTP running on port 69. So on a local system, we can see what ports have been opened up by services that are listening for some kind of incoming service request. But just because something has an open port on the system doesn't mean that clients can get to it. If the host's firewall is enabled, it can still block access to a given port, even though it's open locally. We can take a look at that with UFW status. My firewall happens to be disabled. If I enable it with sudo UFW enable, I can see the status of currently active rules. If something shows up as being open when you look with the SS command, but it doesn't have an open port here, clients won't be able to connect to it. And of course, if there's an open port on the firewall, but no service running locally to respond to requests, that service won't work either. If you're trying to evaluate what network services are running on a remote system, you can use the Nmap tool. I'll install that and run it on my local system here. I'll write apt install Nmap. The Nmap tool can run port scans against a system to see which ports are open. Port scanning can be considered hostile, so be mindful of that when you run Nmap. I'll just scan my own server here with nmap-s-u-s-t and 10.0.2.10 to scan for both UDP and TCP ports. All right, I can see the same ports that I saw earlier are open. That's not too interesting, but if we were running this against a remote system, we'd be able to not only test basic network connectivity to the system, but also see what the firewall is allowing through from the client's perspective. And that can be helpful to determine if a service is available. If you're troubleshooting a service, this can be a helpful set of tools to keep in mind. In addition to the client and server logs, I've definitely spent time trying to figure out why clients couldn't connect, only to realize that the firewall was blocking the port I needed, or that the service hadn't started for some reason.
That's been a look at some common services that enable a network to function well. Each of them is a whole topic unto itself, so be sure to look for our deep dive courses for more information. Take some time and configure networks in different ways to extend your practice. See you next time.